And we'll get started. Good morning, everybody. Welcome to the May edition of Trainee Talks. This will be our final webinar before we take a little break over the summer. So as most of you are already well familiar, Trainee Talks is a monthly webinar series showcasing the research topics of CREATE SE4AI graduate students in their area of expertise related to software engineering and AI. My name is Lori Akiyama. I'm the program coordinator for CREATE at Concordia University, and I'll be moderating the webinar today. So today we are very proud to welcome two master's students from Queen's University, Jiawen and Shenyu, who will be sharing their research with us. Jiawen Liu is a master's student at Queen's University and a member of the Software Evolution and Analytics Lab under the supervision of Dr. Ying Zhou. Her current research focuses on using large language models to generate code explanations with a particular interest in prompt engineering. Jiawen will be sharing her work on understanding open source contributor profiles in popular machine learning libraries. And immediately following Jiawen's talk, we will hear from Shenyu Zheng. He is a master's student in software engineering at Queen's University, co-supervised by Professor Bram Adams and Professor Ahmed E. Hassan. His research primarily explores the performance and correctness of modern artifact-based build systems within a CI context. Shenyu will be presenting his talk on the performance and hermeticity of artifact-based build technologies. Each speaker will speak for 20 minutes, and then, as usual, we will open up the floor to audience questions for 10 minutes. The webinar is currently being recorded and will be available to view on our CREATE website at se4ai.org and also on our YouTube channel. So with that, I will turn things over to Jiawen for her presentation. Jiawen, take it away.
All right, thank you. Let me share my screen. Oh, the wrong one. Screen two. Wait. Okay. Is my slides visible now? Thank you. So, hello everyone. My name is Jiawen Liu, and I'm a master's student from Queen's University. And today I'm gonna introduce my work about understanding open source contributor profiles in popular machine learning libraries. So, first of all, open source software is now a dominant model in software development, preferred by many developers and companies. And the OSS community compromises developers and users distributed all over the world, and who shares knowledge and collaborate on the software development and the maintenance. And they can contribute in many ways, such as writing source code, reporting issues, doing code reviews, and these activities are critical to the success of OSS development and evolution. And many existing studies have tried to understand the OSS contributors from many aspects, such as the volume contribution, identifying their expertise, social networks, identifying long-term contributors, etc. But few have actually tried to combine multiple aspects and provide a comprehensive understanding of OSS contributors. And this is sort of what we aim to work on. And since developers are the most important resource in the software development, and so a deep understanding of the contributor teams would greatly benefit the OSS management, especially because the contributors are distributed far away and they have diverse backgrounds. So it brings more difficulties for project managers to understand their team well and foster a efficient collaboration. And as previous study report that OSS contributors are facing challenges on their collaboration because of different time zones. So it's hard to manage time for discussion or mentoring newcomers, and the differences in language, culture, background knowledge. And there are also barriers for building collaborations. And this motivated us to conduct a comprehensive study on the OSS contributors and help them to promote efficient collaboration. And additionally, as now ML is getting extremely popular and many traditional OSS developers start to learn machine learning and contribute to ML projects. And there are existing studies on ML developers, and which are mainly really using like user surveys and interviews to understand their motivations for learning ML, their experience, and the challenge they have faced. Although this qualitative study have provided very valuable insights, but it is still difficult to make it large scale and have quantitative data to support it. Therefore, our goal of this work is to conduct an empirical study that gives a comprehensive understanding of MLOS as contributors and their activity and the characteristics. So yeah, this is an overview of our approach. We collect ML projects from GitHub and extract the contributors in this project as our subject data. And we extract contributor features based on their activities and contributions to a project. And with this feature, we will first construct a contributor profiles as our basic categorization of ML contributors. And we will further understand their characteristic, and we study the characteristic of this profile from 3 aspects, including their workload composition, their work preference, and the technical importance. So next, I will begin with the data collection. So we select 6 popular machine learning libraries, including TensorFlow, PyTorch, Keras, MXNet, Seno, and Onyx as our subject projects, because we believe these libraries would contain more ML experts, and they usually have a larger size than the project that's implement a single machine learning model to solve a problem. And all these selected projects have like more than 2,000 commits and 7 years of history. So they actually contains rich information that we can leverage. And from all 6 projects, we identify 7,640 contributors, and we were able to extract 31 features from their activities. Next, I will go into construct the contributor profiles and categorize the group of contributors with similar behaviors. And we further study the common characteristic of each profile as well as their differences. So to group the contributors with similar behaviors, we first select like four features that captures the key contributor behaviors. So like the work time captures the contributor's working habit, and number of commits captures the contributors like overall volume of contribution, and code contribution density indicates whether the contributor would like to make small change and simple change each time or a big and complex change. And the number of programming languages capture the contributor's technical expertise, because in our case, it can also reflect the proficiency in different ML components, because like different components are usually coded with different languages. For example, tensors and graph computations are usually coded with C++, so it's faster, and the API implementations are usually in Python. And next, we apply like 8 clustering algorithms to group contributors based on our selected features. And we use silhouette score to evaluate the clustering results and select the result. And we select the results from spectral clustering because it has the highest silhouette score. And we built 4 profiles based on the 4 clusters. Yeah, these are the 4 profiles that we have identified, like core work hour, core after hour, prefer work hour, and prefer after hour. And the naming of each profile is based on their performance in each of the clustering features. You can see that like these 2 profiles in green and orange color have higher total commits and code contribution density and programming languages. So we name them core profiles, and the other two profiles like peripheral profiles. The core and peripheral profiles then further divided based on their work time. You can see that these two profiles in the green box, they tend to make contributions in the normal work hours, and they contribute maybe like work-like manner. And so we name them work hour contributors, and the other two profiles like after-hour contributors. So to understand the characteristic of contributors in each profile, we built 4 logistic regression model to model each profile. So like in each model, we use binary labels where one profile is labeled as 1 and all others are 0. And we model the relationship between each contributor feature and the profile. So you can see that these up and down arrows indicate whether the increase of a feature would increase the likelihood of being a profile. And these stars and dots represent the significance of the features in the model. And as a result, we find that duration, the number of authored files, time zone, and the number of collaborations are the common important features for all profiles, with duration, authored files, and collaborations mainly differentiate from core and peripheral profiles, and time zone differentiate work and after-hour profiles, indicating that the impact of geological location on the contributors' working habit. And then we also use Mann-Whitney test to compare the contributor features for different profiles. And we find significant difference between core after-hour and core work-hour profiles. You can see that although both core profiles make more contribution on all type of OSS activities than peripheral contributors, we still find that core after-hour contributors showing more contribution on the commit-related tasks, like more authored files or code commits, while core work-hour contributors make more contributions on the issue and pull request-related tasks. So therefore, we think core after-hour contributors focus on developmental contributions, while core work-hour contributors participate in both developmental and collaborative activities. And next, we're going to study the workload composition of each contributor profile. So as we assume that a contributor can have different workloads at different periods, and the workload could remain stable over short periods. So the first we do is that we break the project lifetime into different periods of 90 days. And this window size is after the sensitivity analysis. And for each contributor, we first identify their active periods where they have made any type of contribution within the period. And then for each active period, we construct a 5-dimensional workload composition vector, including the contributors' number of issues, issue comments, commits, pull request comments, and code reviews made within the period. And we believe these 5 dimensions are the 5 key aspects of the OSS engagement. And we also normalize the vectors, so it's representing the ratio of each workload instead of the absolute number. Yes, so for each period, we construct a workload composition vector. Then we use hierarchical clustering to cluster all the workload vectors based on their cosine similarity to identify the workload composition pattern. So the higher cosine similarity between 2 vectors means 2 contributors have similar workload in a period, and they should fall into the same pattern. And we determine the number of patterns based on the Sedgwick score and our manual investigation on the clustering results. So As a result, we obtain 5 workload composition patterns, and this diagram shows the characteristic of each pattern. And it's very straightforward that like issue reporters only work on raising issues and barely work on other activities. Issue discussants only work on discussing issue reports, and committers only make commits and do not participate in other activities. And collaborative committers work on both pull request discussion and commits, and code reviewer only work on code reviews and pull request discussions. So we study the distribution of different workload composition in each profile and use chi-square tests to compare the distribution between profiles. And we first find that the committer is the most common workload pattern in all profiles, which means that the majority of our contributor is still focusing on making commits. Oh yeah. But the second most common pattern for core contributor is collaborative committer, which means they often engage in a mix of coding, mentoring, and project management activities. Well, the second most common pattern for peripheral contributors is issue reporters, which means that peripheral contributors may contain a greater proportion of ML users who contribute because they want to solve a specific problem. They use the project. When they use the project, they observe the problem, or they have a specific demand for a specific feature. So that's why they came to contribute. And then we study the important factors for workload composition to the increase of the project popularity in terms of star ratings and forks. So in this way, we build a mixed effect model to model the increase for stars and forks in each period for each project. And the independent variables here are the workload composition related features. And from the model results, we observe that the ratio of issue reporters in the project and the ratio of code reviews made by issue discussants and committers, they have a significant positive association with the project popularity. And which means that if there are more people that's raising issues in the project, and if current contributors who focus on focus on issue discussion or committing to review the pull request, this would help create a welcoming environment and may attract more popularity. So we then study the evolution of different workload composition in different projects as different developmental stages. So in this way, we sort the number of contributors in each workload pattern in a project at different periods into a time series, and also the same as the ratio of contributors in each pattern in each project. And then, so we use the Cox-Stewart train test to examine whether there is significant increasing or decreasing trains in this time series we just built. And we find that the committers and the code reviewers are more sustainable role as the project development progress. As you can see in this middle green box, that both the number of committer and its ratio are showing either increasing or like remain unchanged in the overall trend for all projects. And for code reviewers in the long green box, you see that all projects have increasing code reviewers, both in their early to middle stages and their like entire project lifespan. It's 3 out of 6 projects increasing, others remain unchanged. So they're kind of sustainable than other workload composition patterns. Well, the issue reporter patterns is less sustainable because as in the red box, you can see that the 5 out of 6 projects have decreasing issue reporters as the project development goes. So then we study the evolution of workload composition for each contributor in each profile. Again, we source the contributor's workload composition pattern in each period into time series and apply Cox-Stewart train test to examine if there is significant increasing or decreasing trends. And we observed that only very few contributors, like roughly 2% of the population, shows the significant trend in their workload composition. And all of these are very long-term contributors that they have contribute to the project for at least 2.5 years. And among these contributors, the majority is shifting to the workload that's requiring higher technical expertise than their beginning ones. For example, from issue reporters to committers, or from committer to code reviewers. And next, we study the contributors' work preferences, as the workload composition provide a static view of contributors' behavior in a period. Work preference captures the dynamic behavior in a period, such as whether a contributor prefer to make a peak contribution in a short time, or they would like to make a consistent contribution every day. So here is the detail. So the first step is still the same as how we identify workload composition pattern, that we break the project lifespan into periods and identify active periods for each contributor. And then for each period, we build a time series for the contributor's daily activities by summing all its activity in a day. For example, in this figure, the contributor raised 1 issue report and make 2 commits on day 1, so the first value of the time series will be 3, and so on and so forth until day 90. And then we extract the time series feature from the time series we just built. We extract 9 time series in total. You can see the first 4, they're being entropy C3123 measures the complexity of the time series. The higher feature value is more complex contribution dynamics. And this number of peaks measures the peak contributions in the entire time series. And the longest strike above and below mean measures the number of continuous high contribution and the length of continuous inactivity. And diverse and balanced measures the number of different type of contribution and the balance of the contribution of the contributor made in this period. And in the end, for each contributor, we extract 9 work preference features for each period. And then we again use Mann-Whitney test to compare the work preference features across different profiles. And we find that core contributors tend to have more complex contribution dynamics and make more peak contributions, while peripheral contributors make more balanced contribution across different type of OSS activities. But the work preference difference between the work hour and after hour subgroups tend to be negligible. We then study the relationship between the contributor's work preference and the project popularity. Same as what we did for workload composition, we build a mixed effect model to model the association between work preferences and the stars and fork increase for each project in each period. And we find that contributors more balanced contribution across different type of OSS activities and make more code reviews is positively associated with both star and fork increase. So then we study the evolution of contributors' work preference for each profile. So the same as what we did for workload composition, we sort the contributors' work preference features in each period into time series and apply Cox-Stewart train test to examine if there is significant increasing or decreasing trains. And similar to our findings before, only a small portion of contributors, roughly like 5% of contributors shows significant trends in the shift of work preference features, and all of them are long-term contributors. And these two figures shows the work preference trend for the two core profiles, with the blue color indicates the positive trends, and the negative indicates the amount of contributors with negative trends. And we find that only longest inactivity time, balance, and review, these three features are dominated by increasing trend, and all other preference features are dominant with decreasing trends. Therefore, we find long-term contributors tend to shift towards more constant and balanced contributions. And lastly, we study the technical importance of the contributors in each profile. So this shows how we measure the technical importance. Is that we first build a graph or a network of the repository for each project, where the folders and the source code files are nodes, and the relationship of a folder contains a file as edges. And since eigenvector centrality are very commonly used to measure the importance of a node in a network, so here we can use eigenvector centrality to measure the importance of each source code file in the project. And then we measure the importance of a commit by averaging the importance of the files that is modified by the commit. And our rationale here is that more important commit changes the more central and more influential files in the repository. And lastly, we measure the technical importance of a contributors in a period by summing the importance of the commits made by the contributor within the period. And therefore, this period importance considers both the importance and also the amount of commits made by the contributor in a period. Then we introduce 4 technical importance matrices. And the first one, max commit centrality, is the importance of the most important commit of a contributor. Max centrality day is the number of days taken before the contributor reaches the most important commit. And max period centrality is the importance of the most important period of a contributor. And the max centrality period is the periods before the most important one is reached. So then we apply the meant-when-need test to compare the technical importance matrices across profiles. And we find that the core contributors tend to reach higher commit importance and the period importance than peripheral contributors. And the core contributors also tend to take longer time to progress to the maximum technical importance. Usually they take 6 months on the medium to make their most important commit. And while peripheral contributors, they tend to show the maximum technical importance upon they join the project. So they actually do not progress to higher importance at all. So lastly, we explore the evolution of contributors' commit importance and period importance for each profile. And again, we find that only a small portion of long-term contributors, like roughly 10% of population, shows significant trends in their commit importance, and roughly 5% shows the significant trends in their period importance, and the rest just remain unchanged, or they do not show significant change. And like roughly similar amount of contributors showing increasing and or decreasing commit importance. But you can see on the right that the period importance is dominated by the decreasing trend. And therefore, we think these long-term contributors tend to shift away from the intensive and highly technical contributions. Yeah, that's what we have for today. Any questions?
Thank you very much, Jiawen. Does anyone have any questions for Jiawen? We're running a little behind, but we have time for one or two. So Bram, please start us off.
Yeah, thank you for the detailed presentation. Lots of a lot of analysis there. Great. So I'm wondering. So the title was about basically machine learning libraries and to see how people contribute in these kind of things. So I'm wondering, what are your findings like in terms of these profiles and preferences and technical impact compared to like non-machine learning libraries, like traditional open source? Did you observe any differences in the way people work or what kind of contributions
actually, we're not including any like non-machine learning libraries in as our data set. So we actually didn't make any comparisons within this work.
Ooh, yeah, because I think that would be interesting future work to see if there's actually a shift there.
Yeah, I think that's interesting too.
Cool. Thank you.
Maybe just to piggyback on Dr. Adams' question, but just to ask in a different way. So, do you know, like, what would you say is special to machine learning, these machine learning libraries? Like, what is one or two findings that you would say this really applies to these machine learning libraries?
I think our analysis does not like really contain any ML specific concepts that I can report that it's only happening in machine learning. We actually conducted it as like empirical study on the software, so traditional software projects, but just our data set is like all machine learning experts or contributors.
Okay. But I mean, your initial data set is ML libraries, right?
Yeah.
So it's not just traditional software. I mean, you are specifying on that, or am I misunderstanding?
I think we're just like reporting like our findings in a traditional software analysis on the machine learning contributor data set.
Okay. All right. Thank you.
Thank you.
Okay, last question, Hassan.
Thank you so much for the presentation. It was a lot of analysis. Well done. I have a clarification question. So the main criteria for splitting the profiles was based on the work hour or if it's after hours. So my question is, this is something that I missed. What have you considered as the reference point of time to consider if the contributor is working after hour or work hour? Is it the time zone of the contributor or is it the time zone of the project? And do you think that how this might affect your findings? I mean, I know that you may not have the results of this analysis, but how would you expect the results to change?
You mean like my criteria
yeah,
for...
the profiles we have work hour and after hour. So
it's based on like the local time of the author make their commits.
And let's say that I'm a contributor and the project is in another time zone and I try to adapt myself to that time zone. I try to work at the time that the other developers are active. So
yeah, that will be considered working after hours because it's trying to adapt to a different time zone, and it also shows that which like time zone kind of leads the ML.
Okay, great. Thank you.
Yeah.
Okay, thank you very much, everybody. I think we should proceed directly to Shenyu's presentation. So Shenyu, please go ahead and share your screen. And thank you once again, Jiawen. That was great.
Okay, thank you. So yeah, wait a second. So can you see my screen now?
Yes, we can see your screen.
Okay, got it. Okay, so then now. Okay. Hi, all right. So my name is Shenyu. The topic of my today's talk is on the performance and hermeticity of artifact-based build technologies. So to begin with, let's first talk about CI. CI is a practice of frequently integrating code changes into code bases and tracking the quality of the integration through automated builds, performing building and performing compilations and testings. So CI is a widely used practice in industry. Actually, according to a report by City Foundation, 83% of surveyed developers are involved in DevOps practice, and CI is the core component of DevOps. Another report by JetBrains pointed out 44% of the surveyed developers confirm regular usage of CI/CD tools. So CI is not just widely used in industry, it also benefits the development effectiveness a lot. A report by Google Cloud suggests organizations that have mastered CI/CD deploy 208 times more often than the rest. So despite the widespread usage of CI, it is important to ensure CI to be efficient to fully utilize it. Ideally, CI pipelines should finish timely. Otherwise, long CI builds will delay the feedback of the integration and slow down the development activities. Moreover, the results of CI pipeline should be consistent so that they can be trusted by developers. Many techniques have been proposed to ensure CI to be efficient, such as test selection, build scheduling. However, build technologies as the core component and the most fundamental component of CI pipelines is the least analyzed factors. It's one of the least analyzed factors. The underlying build technologies run by these pipelines have to be fast and reproducible to make the CI pipelines to be fast and reproducible. So how do these build technologies achieve a fast and reproducible build? To understand that, we first need to understand how build technology perform a build. So during the build process, the build systems analyze the internal and external dependencies of the projects, then generate a DAG. According to the DAG of compilation units, where each unit represents a compilation task. According to the DAG, the build system determines how to carry out the build. So traditionally, there are two major techniques that are offered by build technologies to improve build performance. The first one is parallel build. The second one is incremental build. Without any optimization, assuming the build time of each compilation unit is 1T, the total build time is 11T. With parallel build, which build projects in parallel, the build time can be reduced from 11T to 40 in this case. With incremental build, which only build changed paths, in this case, there are changes happen to the leftmost node in the DAG. The build time can be reduced to 2T. While this build performance feature sounds promising and beneficial, it is often challenging to achieve a fast build using these techniques in traditional build technologies. So one of the major reasons is the absent dependency information is difficult to identify in these build technologies. So as it often these undeclared libraries and the internal dependencies often lead to inaccurate dependency graph, therefore inaccurate parallel and incremental builds. Oh, now we go to now we start to introduce artifact-based build technologies. So in recent years, a new family of build technologies have emerged, which is artifact-based build technology. In artifact-based build technology, it requires developers to explicitly specify all artifacts and all their internal and external dependencies in the build configuration files. Since all dependencies have to be specified, it can generate an accurate dependency graph, therefore provide reliable parallel and incremental builds. In addition, it also provides built-in support for reproducible builds. A build is reproducible when given a same set of source code, same build environment. It always produces produce bit by bit identical copies of artifacts. So in artifact-based build technologies, they enable reproducible builds through a technique called hermetic build. So what is hermetic build? The idea is actually very simple. So the build system provides a self-contained build environments and perform the build within the build environment. So the self-contained build environment is achieved through build isolation and build dependency management at build 2 level. Since the build is isolated, the changes made to the host system cannot impact the build within the build environment. Since all the dependencies are managed by build system, therefore, any access to these undeclared libraries can be detected, since these libraries are not like are not specified and are not within the sandbox. Therefore, artifact-based build technologies are able to provide reproducible builds. Okay, despite this promise, despite their promises, it is unclear to what extent this artifact-based build technologies fulfill their promise. For parallel build, it is often developers only get suboptimal parallelism due to the hardware resource limitations. For example, despite your artifact-based technology may provide up to 16 parallelism degree of parallelism, you only have 2 cores on your machine, so there is upper limitation. In addition, the poorly organized project structure may also handle the utilization of parallelism. For incremental build, downloading or uploading caches could be more time-consuming than the build itself, especially when there are a lot of small files to be cached. For hermetic build, the hermeticity of the build process relies on the hermeticity of the underlying build rules. However, these build rules may not be reliable, especially when they come from open source community. A recent study pointed out developers may abandon Bazel, which is the most popular artifact-based build technology, if the benefits do not justify the maintenance costs. Therefore, in this research, we focus on we argue artifact-based build technologies such as Bazel have substantial potential for reducing build times and achieving hermetic builds. In the research, we focus on 2 parts of the Bazel. The first part is build performance part. So in first article, we analyze the usage of build performance features in CI. In the second and third article, we evaluate the impact of these build performance features on the build times. In the second part of the research, we focus on the hermeticity side of Bazel. The first article evaluate how hermetic are Bazel builds. The fifth article understands the reasons for non-hermeticity introduced in the build process. And the last article tries to understand the impact of build hermeticity. So we use source graph to collect the Bazel projects from GitHub. We exclude the projects with less than 100 stars and commits to remove tribal projects. After we employ automated tools and manual examination to remove false positives, we collected in total of 383 Bazel projects. In addition, we also collected 383 small Maven projects, 383 large Maven Bazel projects. And we use them as the baseline for comparison in our arq1 to say what is the difference in build performance usage between traditional and modern artifact-based build technologies. In arq1, we focus on the usage of build performance features in CI. Therefore, we analyze 3 most popular CI cells in GitHub, which are GitHub Actions, Circle CI, and Travis CI. In addition, we also analyze build kite, which is popular among Bazel projects. We identify CI configuration files from projects, and then extract cache-related configs and Bazel or Maven build commands. So in arq1, we found parallel and incremental build features are more commonly used in Bazel projects than in Maven projects. As shown in the figure, all Bazel projects employ parallelization, where a few Maven projects did that. Although the usage of cache are similar between Maven and the Bazel projects, we found Bezier projects mostly use build-to-specific cache, while Maven projects use general-purpose CI cache. So the build-to-specific cache is provided by build technology itself. It is usually tailored for build technology and provide better performance and more security than general-purpose CI cache, which is provided by CI service. Moreover, we found most Maven projects only cache the dependencies. So they are not used in incremental build because the build results are not cached. While Maven projects cache both dependencies and the results. Despite the more widespread usage of build performance features in Bezier, these build performance features are still not fully utilized. As shown in the figure, more than half of the Bezier projects do not use incremental build feature at all, despite Bezier's strong claim to provide strong support for incremental build. Actually, we found there are 30% of Bezier projects do not use Bezier at all in CI pipelines, compared to the high usage of Maven in CI pipelines. In Arc2, we perform experiments to understand the utilization of Bezier's parallelization feature. From previous collected Bezier projects, we identified 70 buildable Bezier projects. Then we perform experiments for each project. We clone the latest for each project. We clone the latest snapshot, and build them within Docker container using different CPU quarter to understand the get the build duration at different parallelism degrees. So after the experiment finished, we retrieve and analyze the build logs to get the build times. In total, we performed 3,500 experiments, and we collected build times for Bezier projects with parallelism degree 1, 2, 4, 8, and 16. So this figure shows the speed up of builds for different parallelism degree. The speed up is calculated based on the build time with parallelism degree 1, which is a sequential build. So we found Bezier's parallel build feature has potential to greatly reduce build times, particularly for long build duration projects, as the median speed ups for long build duration projects is 3.84 times at parallelism degree 4, 7.36 times at parallelism degree 8, 12.8 times at parallelism degree 16. However, the improvements in build time slow down after reaching a certain level of parallelism, especially for medium and short build duration projects. So as shown in the figure, the speed ups for medium and short build duration projects at parallelism degree 8 are not significantly different than their speed ups at parallelism degree 16. So the speed ups for these two types of projects slow down after reaching parallelism degree 8. So actually, as the parallelism degree increased, we found fewer projects fully exploited the parallelism. To help developers to better utilize Bezier's parallel build feature, we perform additional social network analysis on the DAGs of these projects to try to understand how can developers to improve the utilization of parallelization. And we found improving the software structure does not necessarily improve the effectiveness of parallelization. However, reducing the granularity of artifacts, which is reducing the granularity of the compilation units, is shown to statistically significantly improve parallelization efficiency at a parallelism degree of 16. In Arc3, we perform experiments to understand the utilization of Bezier's incremental build feature. So we perform experiments on the same set of buildable projects, and for each project, we retrieve its last 100 commits and build each commit within Docker containers using 4 cache strategies. The first one is clean, which is build projects without any cache. This is used as the baseline to calculate the speed up. And this, then we use general purpose CI cache to cache in our second and third strategies. As we mentioned before, the general purpose CI cache is usually provided by CI service. We use fuse file system to mount object storage onto our Docker container to simulate it. the build systems within the Docker container will access the cache files stored in the object storage through fused file system. So for the second strategy, we only cache dependencies, and for the third strategies, we cache both dependencies and the results. For the last strategy, we use build2 specific cache to cache both dependencies and build results. We set up a Bazel cache server on another machine, and the build system will access the build2 specific cache through gRPC API, and the build cache server will access the cache stored on object storage underlyingly. After the experiments are finished, we collected the build logs and extract the build durations. In total, we performed 102,232 experiments, and we collected the build time measurements for Bazel projects with 4 cache strategies. So the results show. So this figure shows the build times, the speed ups for using different cache strategies. We found using incremental build significantly improved the build performance for medium and long build duration projects. For medium build duration projects, the median speed ups are 1.21 times and 1.25 times with large effect size. And the median speed ups for long build duration projects are 2.22 times and 2.71 times with large effect size. However, using incremental builds are not very effective for short build duration projects, as it only show a negligible and small effect size using general purpose static cache or build2 specific cache for incremental builds. In RQ4, we analyze the hermeticity of Bazel build process. Similarly, we perform experiments on the 70 buildable Bazel projects. And during the build process, we use strace to collect the Linux file system calls happened during the made during the build process. Then we extract the files accessed in the build process by analyzing the strace logs. Then identify their corresponding build dependency packages. Lastly, we identify if these packages are executables run by the build systems, or they are files read by this build system. Only files like read or write by this build systems. As a result, we collected the hermetic and non-hermetic build dependencies, hermetic or non-hermetic torsions and libraries accessed in the build process. So all results show none of the projects had a completely hermetic build. As you can see from the figure, all projects show a non-hermetic build process as they access the files that are not managed by the build systems. We perform further analysis to say what kind of build dependencies contribute more to the non-hermeticity, and we found the number of top-level torsions contributed the most, as the number of top-level non-hermetic torsions is significantly higher than the number of top-level non-hermetic libraries. Then we found these non-hermetic torsions are mainly caused by the default configuration of Bazel build roles. For example, the default configuration of root CC and root Python, which are Bazel's official build roles, uses the host installed GCC and Python. Moreover, we found even if these build roles use hermetic torsions, it may still access non-hermetic files, and we identify 4 such instances. So we found the Bazel build process is not hermetic, and there are reasons. We also need to understand why they are important. Therefore, we analyze this. We perform further analysis on this non-hermetic build dependencies. So this figure shows the number of dependencies that are included or not included by default in a standard Debian installation. We found projects contain a median of 12 non-hermetic dependencies that are not included in standard Debian installation. This means if you perform the build on a new machine, and you do not install these non-hermetic dependencies manually or through script, there is a high risk your build will fail. In addition, we also analyze the update frequency of these non-hermetic torsions within side-round images. So in major size surveys, these side-round images are usually not managed by developers. And this side source providers may update the dependencies installed in these side-round images at any time. So the build may also risk to fail if this or result in inconsistent build results if this non-hermetic build dependencies are updated by service providers. Actually, we found the median number of updates in last 3 years for top level libraries is 11 and 9 in GitHub Actions Ubuntu 2004 and 2204 round images respectively, and the corresponding numbers for COCS Ubuntu 2004, 2204 round images are 3.5 and 3 respectively. To conclude, we found Bezo's parallel and incremental build features can significantly reduce the build times inside for certain type of projects. For example, the median speedups for long build in projects using parallel build is 2 at 2, 3.84 at 4, 7.36 at 8, and 12.8 at 16. And the speed ups and the median speed ups for long build duration projects using incremental build is 4.22 using general purpose set cache and 4.22 times and 4.71 times using build to specific caches respectively. However, the improvements of parallel build slow down after reaching a certain level of parallelism, and the improvements of increment build may not increment build may not be very effective for short build duration projects. We also found Bezo can ensure hermeticity. However, achieving this requires a lot of effort, as non-hermetic builds are often caused by the default configuration of build rules. To modify to make the build process to be hermetic, we need to modify these default configurations, introducing extra maintenance costs. Given Bezo's already very high maintenance costs, modifying this default configuration can introduce, even more maintenance costs. So the work presented in the slides come from 2 papers. The first one is does using Bezo help speed up continuous integration, which was accepted by EMC, and the other one is on build hermeticity in Bezo-based build system, which is submitted to IEEE software. And thank you. Any question?
Thank you, Shenyu. Excellent presentation. Does anyone have any questions for Shenyu before we wrap things up for today? No questions, really? I had a question at the beginning. What is hermeticity? Because I'd never heard that word before. But I'm not sure that I fully understand the concept even after.
Yeah, this is like a very new term. So basically, hermeticity is like how well the build is isolated and isolated from the outside environment. So
Okay.
Yeah. So basically, if a build is hermetic, it means the build will only access the files that are managed or that are managed by the build process, and the build process that are managed by the build system, and the build process will only and the build system and the build process is isolated from the host system. So basically, like kind of isolation and the build dependency management. Yeah.
Okay, thank you.
Okay.
Great. Okay. So if there are no further questions, I guess we'll close the trainee talks for today. But thank you so much to everybody for joining. Thank you especially to our 2 speakers, Jiawen and Shenyu. I think you're both graduating soon, so best of luck as you finish up your master's studies at Queen's. And really looking forward to seeing everybody very soon at our CREATE retreat in Kingston.
Thank you.
Thank you.
Thanks, everyone. Have a great day.
Yes.
Thank you, everyone. Bye.
Bye.